Our sun is a pretty normal star. It's relatively average in size, temperature, brightness, and mass. This may seem boring, but it's these characteristics that allow our sun to be stable enough to support life on Earth, and will be able to for billions of years. But what happens if we crank everything up just a little? Well, before long, we get into a whole new category of stars. Stars that become so big, they put our sun to shame. Now, before we get into these huge stars and how they get that big, I would appreciate if you would like the video, subscribe to the channel, and hit the notification bell to stay tuned for future content. Okay, so in order to talk about giant stars, we need to talk about two major things: a star's mass and its life cycle. Stars may look like static and unchanging objects, but over timescales of millions of years, they evolve. How they evolve is dependent on how massive the star is. Stars that are less than half the mass of the sun have pretty uninteresting lives, as they are small red dwarf stars that burn continuously for billions, even trillions of years before they quietly flame out. Interestingly, these red dwarfs are the most common type of star in the universe, thanks in no small part to the low barrier for entry. Things get more interesting when we talk about stars between 0.5 and 8 times the mass of the sun. Despite the huge range, these stars all have very similar life cycles. For hundreds of millions to billions of years, they burn hydrogen deep in their cores, and thus are stable main sequence stars. After the hydrogen in their cores are depleted, the star expands a lot as they enter their so-called red giant phase. Contrary to what you may think, these stars are comparatively cool, with temperatures less than half of what the sun is today. These stars are often 50 to 200 times bigger than they were in the main sequence, though they remain that big for only a few million years before they expel their outer layers and become dead husks again. In the case of our sun, it will become a red giant itself in about 7 billion years, and it may become so big, Venus, Earth, and maybe even Mars will get destroyed. Though this all depends on how much the planet's orbits expand, as the sun will be far more unstable and will be undergoing extreme mass loss during this time. The actual timescales of these events vary depending on the mass of the star, from 50 million to 50 billion years, but the actual sequence of events is roughly the same. So, what happens when stars are more than 8 times the mass of the sun? Well, this is when things get fun. These stars are the brightest and hottest main sequence stars of the bunch, with temperatures 5 to 10 times hotter than the sun. You would expect more massive stars to live longer, but the rate at which they burn fuel greatly outpaces the increase in actual fuel to burn. As a result, these stars are only on the main sequence for a few million years, in some cases shorter than the time early human ancestors have existed. Once off the main sequence, things get a lot more complicated, and the determining factor is, you guessed it, mass. There are honestly a ridiculous number of paths these stars can take, so many that I can't cover them all here, but there are 2 major routes. The first route is pretty simple. After exhausting the core hydrogen, the star begins to rapidly expand and cool just like their smaller counterparts, eventually becoming the creatively named red supergiant. These stars are monsters. The most well-known instance of a red supergiant is the star Betelgeuse, in the constellation Orion, about 500 light-years from Earth. This star has a radius of 5.5 astronomical units. Don't know what that means? Well, the average distance between the Earth and the Sun of 93 million miles, or 150 million kilometers, is 1 astronomical unit. Jupiter orbits at a distance of about 5.2 astronomical units from the Sun. In other words, if Betelgeuse replaced the Sun, even Jupiter would get eviscerated. Stars like Betelgeuse generally have a million years or less before they die. So what exactly is happening in this time period? Well, for a few 100,000 years, red supergiants fuse helium into carbon in their cores. This happens to some-like stars as well, but the difference here is that their cores can never get hot enough to fuse heavier elements. The pressure is definitely there for bigger stars though, so they are able to keep going. Carbon is fused into neon for a few thousand years, neon fused into oxygen for a few hundred years, oxygen fused into silicon for about a year, and finally it takes a single day for silicon to fuse into iron under temperatures of several billion degrees. Once the core is iron, it cannot be fused into anything else, so the outward pressure keeping the star semi-intact disappears. The star's huge envelope collapses into the core, then violently bounces off of it in a supernova explosion that emits more energy in 1 second than the sun will do in its entire life. It outshines entire galaxies, and it is possible for supernovae in neighboring galaxies thousands of light years away to be visible to the unaided eye on Earth. What is left is generally a neutron star, an ultra-dense, neutron-filled core that is about 2 solar masses packed into an area the size of Manhattan. This is the route that stars take when they just barely clear that 8 solar mass threshold to go kaboom. But what happens if they clear it by a more substantial margin, say 30 or 40 times the mass of the sun? Well, the route they take starts out similar. They become even bigger red supergiants, so big that they need to be called red hypergiants instead. The biggest star known, Stephenson 218, falls under this category with a staggering 10 astronomical unit radius, which is over 2,000 times the radius of the sun and past the orbit of Saturn. These stars don't just explode as red hypergiants, though. Instead, after the helium fusing process, they shed their outer layers and become a hotter, smaller star called a Wolf-Rayet star. These stars are among the most unstable in the universe, with regular outbursts that dramatically increase the star's brightness and lower its mass. After going through the same core fusion processes as the lower mass stars, they explode even more violently, with the collapse so powerful it actually creates a small black hole in its wake. Certain stars with high rotations will cause gamma ray bursts from their poles, essentially energy beams so energetic they can fry the atmospheres of planets thousands of light years away. Thankfully, as far as we know, no such stars are pointed at us, and none like we have been for hundreds of millions of years. So yeah, hopefully this video reminded you that we are very, very lucky to have a star as stable as our sun, as this stability allowed life to develop on Earth in the first place, and will allow it to flourish for quite a while longer. In the meantime, I would appreciate if you would like the video, subscribe to the channel, and hit the notification bell to stay tuned for future content. Thanks and have a great day.